Okay, welcome everyone. My name is Schuppen and I'm a master's student at the Technical University of Eindhoven in the Netherlands. I'm here to present my research that I performed together with my fellow students with the subject evaluation of the net cross-sectional failure of steel plates with different hole configurations in the presence of cracks. So when designing a structure with steel or designing with steel, the Eurocode 3 can be used, which includes a lot of failure modes for steel elements. In this research, class 6.2.3 is investigated, which have different rules for steel elements subjected to tension. When bolt holes are present in steel elements, the net cross-sectional area of the element is reduced, and therefore the net cross-sectional resistance for those plates can be decisive over the cross-sectional resistance. So in this research, okay, the formula 0.9 times the net cross-sectional area times the ultimate resistance of the steel divided by a partial factor is investigated. The partial factor is based on some experimental tests and specified in each country's national annex. For the Netherlands, this is equal to 1.25. But when omitting this partial factor, you get the plane resistance formula, which is the subject of this research. The 0.9 factor is based on several reasons. First of all, some test evaluations on bolted connections. Secondly, some consistency with other rules, but also a fracture mechanics safety assessment. Oh. Yeah, so the motivation of this research is to research the applicability of this plane resistance formula and especially the conservatism of this 0.9 factor, which is included in this formula. In this research, this is investigated for three different types of specimens, type A, B, and D. Type A is one centric hole in the specimen, type B has one eccentric hole, and type D has two staggered holes. In this research, it is especially investigated when small cracks induced by cyclic loading are present. This research is part of a larger research which also investigates different geometries, but also steel grades or the presence of holes in the steel plates. Okay. Should go one back. There you go, one slide back. Yes. Okay, so the material used for this research is of steel grade S275. The stress-strain properties are shown on this graph, and the ultimate tensile strength and yield strength are displayed on the slide. The width and size of the holes in this research are based on previous research, but also on the codes. And the thickness is based on availability because we use the same batch of material as previously performed research by Baarsen. Okay, so all the experiments are performed in the laboratory of the Technical University of Eindhoven, and for both cyclic loading and tensile loading, we use a Schenck hydraulic universal testing machine, like displayed on this picture. For the pre-cracking, we use a crack detection method called the broken wire electronic binary sensor method. I will show that on the next slide as well. The applied load range is for all the three specimens different because they have differences in their cross-sectional area, but also on the stress intensity factors around their holes. For the tensile loading, the same machine is used again, but this is a displacement control test to ensure that we can capture the entire load information of the specimen, as well as to ensure stability and safety during the test setup. This is a tensile failure test, so we will pull the specimens until failure, and also an LVDT is placed around the holes to see the strains around the holes more accurately. Yes, so the cyclic loading is done with this principle. We glued some copper wires next to the walls on both sides of the plate. So and we connected this to an electronic circuit which goes to the controller of the machine. And then if a small crack occurs, it detects a break in the electronic circuit, which will shut off the machine. So the machine will stop after a crack is initiated. Okay, for the tendon test, this is the setup. On the left picture shows the LVDT on the back side of the specimens. The middle shows the machine setup, and the right picture is a picture of one of the specimens during the tensile failure test. The broken wire electronic binary sensor method proved very well to work with very small cracks when they are initiated. The cracks are very small, so we could only visualize them with the microscope, and some of them we showed on this slide. The wire has a diameter of 0.1 millimeters, so there are very small cracks below 1 millimeter. So for the results, I displayed one of the specimen types, so the centric hole specimen type A, with their force displacement graph. You can see that there are large similarities between the non-cracked specimens, because those are the solid lines on the graph, and the pre-cracked specimens, which are the dotted lines. However, there is some earlier nonlinear behavior in the pre-cracked specimens. Also, we calculated a ratio of the experimental resistance over the calculated resistance with the resistance formula to be able to compare the different test results of the 3 different specimen types. So these graphs show the first part of the force displacement graphs for all 3 different types. You can see that there is earlier nonlinear range in the displacement behavior because of some plasticity due to the presence of the cracks. Yeah, so for the ratio of the experimental test results over the calculated results, we plotted them in a histogram on this graph with the solid ones, again the uncracked specimens, and the dotted ones, the cracked specimens. You can see that for relatively small cracks of below 1 millimeter, they do not seem to have an influence on the ultimate resistance, or just a very small one. However, we did have an outlier in specimen D7. If you noticed, this was because of an equipment malfunction. That's why the crack initiated for way too long before the machine shut off. So it has a very low ultimate resistance compared to other specimens. Because this is the picture of specimen D6, which has a very small crack at the left top, which was a crack that we were aiming for. And this shows the depth of the crack of the specimen D7. So it was way too large for this experiment. So for the results, you do see a small decrease in the ultimate resistance of the pre-cracked specimens. And there's also an increased standard deviation in the results. Could possibly be because of different crack sizes which were initiated, and also because we did a relatively small number of tests. We can compare this ratio of experimental results over calculated results by previously performed research. We did this in this graph with results of Baarsen and Kessels. They all have similarly the same results. However, Baarsen has some lower values. They also had some outliers in the crack depths up to 7 millimeters, so that can cause a bit of lower value. Kessels also investigated other skew grades and other bolt hole configurations, but they all came to the same conclusion. So I also put in 3 pictures of the fracture surfaces just to show you. Specimen D4 has multiple cracks initiated. It has 1 surface crack, but you also see the corner cracks at the tops. However, we aimed for just 1 corner crack, like shown in specimen D6. And I also added the specimen D7 just because it looks nice. Okay, we also performed a fracture fault analysis, which is standardized in British Standard 7910. We used option 1 to construct a failure locus, which is the most conservative but also the simplified way. So we only needed the yield strength and the ultimate strength of the material. You can see the failure locus on the left picture. On the horizontal axis, there is the plastic collapse ratio, which is the applied load divided by the ultimate by the collapse load. And on the vertical axis, there is the brittle fracture ratio, which is the stress intensity factor divided by the fracture toughness. If the assessment point falls on the failure locus, failure will occur, or it's above the graph. This slide shows the formulas for the assessment of the fracture toughness, which is corrected for constraint effects on the basis of the master curve. And the top equation is the master curve formula, which estimates the fracture toughness. It needs the T0, which is equal to T27 joules minus 18, and given in the codes. The B is the thickness of the plate, which is equal to 8 millimeters. And the probability of failure is set to 50% to calculate the mean prediction. This fracture toughness is corrected for lower values of T stress when low constraints are at the crack tip. Yes. So for the results of the FOD, we included different crack sizes, like shown here. For very small crack sizes, there is no reduction in the failure load according to this model. Up to until 0.60 millimeters, there is no reduction, after which there will be a small reduction in failure load up to 20% of reductions for 2.5 millimeter crack. However, these results show a similar trend to our experimental results, but they are a bit conservative, which is because we use option 1, which is the most simplified but also the most conservative way. But we also used a simplified way to calculate the collapse load. So for the conclusions, to see if the ultimate net cross-sectional resistance of steel plates with bolt holes is still applicable when pre-cracks are present due to cyclic loading. We have several conclusions. Pre-cracked specimens do show differences in their plastic behavior, so it's less linear elastic than the non-pre-cracked specimens. Also, the ultimate resistance for small cracks below 1 millimeter does not significantly change when cracks are present. So, and also that's why the last 6.2.3 is still applicable for specimens with small cracks. Also, the failure assessment diagram predicts the similar trend, but is a little bit conservative, but can be used to estimate the behavior of other geometries and possibly temperatures or steel grades. So some recommendations. The broken wire electronic binary sensor method that we use to detect the small crack when initiated works very well. Also for steel grade S275, the 0.9 factor can be omitted, which is similar to research performed by Romhaus or Snijder, which all concludes that the 0.9 is too conservative and could be omitted for small cracks for this steel grade. Also, further research can be done on the effect of fatigue for higher steel grades, which are more brittle, but also when multiple cracks are present in one specimen.